So here we'll talk about the traveling electromagnetic wave. So on the left-hand side of the figure, we can see we have the energy source, and yeah, probably it will generate some charges or current, or pumping some energy into the LC oscillator. And in chapter 31, you know that for this RLC circuit, there will be a natural frequency determined by the RLC value, yeah, or strongly determined by the LC value, which is approximately 1 over square root of LC. And after passing through the transformer, it will be a sinusoidal current on the secondary stage. So as you can see here, an arrangement for generating the traveling EM wave in the shortwave radio region of the spectrum. An LC oscillator produces a sinusoidal current in the antenna, which means on the secondary stage. And as you can see, the antenna is here. So, and according to the Maxwell equation, or more specifically the Faraday's law, and also the Ampere's law, or Ampere-Maxwell's law in this textbook. So as you know, as long as there are time varying current here, and according to Ampere-Maxwell's law, or simply the Maxwell's law, this time varying current will generate time varying magnetic field. And this time varying magnetic field, according to the Faraday's law, will generate the induced E field. And this time varying E field will generate the magnetic field, so on and so forth. So this is roughly how the EM wave are generated. And of course, if you really need to know the rigorous derivation, actually we need to really solve or we need to derive the wave equation from the Maxwell equation, and then we try to solve the wave equation. Then we'll know why the this mechanism or this setting will generate the EM wave. And here it mentioned that P is a distant point at which a detector can monitor the wave traveling past. So here we have the P is the distant point, and the distance means it is far away from the antenna. So here on the left hand side, we can see this is a demonstration for the EM magnitude, and it is possibly looking from the right side to the antenna. So as you can see here, it mentioned that for the electromagnetic wave, the E field and the B field change with time as one wavelength of a wave sweeps past the distant point. So the wave is traveling directly out of the page. Now it is assuming the wave is traveling out of the page, which means that for the Y figure, the waves probably is definitely propagating to the right side. So it feels like you see from the right hand side. And then for the left figure, then you will consider this wave is propagating out of the page, but in different moments. So it shows it in like 1, 2, 3, 8 moments from A to H. Okay, so here it also mentioned that we choose a distant point so that the curvature of the wave is small enough to negate the curvature. Because as you can see here, this is the antenna to generate the EM wave, so it is the source, and you can see the wave front is somehow like circular, which should probably be like a concentric circle, which just like you have a stone and throw it into the lake, then yeah, suppose you have a stone, throw it into the lake, and then suppose it's dropped to here, and then you will see the wave propagating to different direction, and then you can see many concentric circles as the wavefront. So this is similar to this case, although that is the wave, the mechanical wave for the water, and here is the EM wave. But here it mentioned that suppose we consider the P is far away from the antenna, which means that suppose the radius of the circle is large enough, and then suppose you consider this part, and here it looks like this is a straight line, or more precisely speaking, it is the wave is said to be a plane wave, on a plane rather than a curvature. And the discussion of the wave is much simplified. So we make this assumption so that we can use some simple equation to describe the EM wave. And on the left side, you can see we have E field and B field with different amplitude and direction. And here we can see there are some observation about the EM wave. So the first point is that here we have E and B field are always perpendicular to the direction in which the wave is traveling, which means that suppose the wave is propagating out of the page, and also you can see here the E field is pointing upward and the magnetic field is pointing to the left side. So which means that the propagation direction is actually perpendicular to the paper, or to the screen. And actually E field and B field are on the screen, on the plane of the screen. So you can see even for A, B, so all the E and B are on the plane, all the E for all these 8 situation. Or maybe you will consider for C and G, both the B field and E field are zeros, but this is just an exceptional case. But for most of the time, almost all of the time, B field or E field are on the screen in this case if the propagation direction of the EM wave are out of the page. So E field and B field are always perpendicular to the direction of the wave propagation. And the second point is that also the E field and B field are always perpendicular to each other. So you can see for figure A, E field pointing to the upward, and B field pointing to the left side. So they are perpendicular to each other. B is also the same. And for D, E, F, E pointing downward and B pointing to the right side. So you can see B field and E field are always perpendicular to each other. So there are totally 3 directions. One is the E field, and another one is B field, and also the wave propagation direction. So all these 3 directions, if you just pick out 2 of them, then they will always perpendicular to each other. This is for point 1 and 2. And then for point 3, moreover, we can also say that the cross product E and B always give the direction in which the wave travels. Here it means that suppose we have the propagation, we have the direction of E cross B using the right hand rule, so that suppose you have for example, for for figure A, and then you use the forefinger pointing upward, which means the E direction, and then you cross to B, so that your thumb will be pointing out of the page, which match this statement 3. And yeah, for B and H, E and B have the same direction, so they are the same. And for D, E, F, in this case, E and B are pointing to the other direction. In this case, E is pointing downward and B is pointing to the right side. So you use a forefinger pointing downward, and then you cross to the B field, so that your thumb is still pointing out of the page, which matches the statement 3. So yeah, so E cross B is definitely the direction of the wave propagation. They will not change the order, which means it is not possible that the wave is propagating out of the page while E is pointing upward and B is pointing to the right side. This is not going to happen. So this is not going to happen. And for statement 4, the field always varies sinusoidally. Moreover, the field varies with the same frequency and in phase with each other. So it is just like, yeah, it tells it is an observation, but actually this is actually the solution for the wave equation. So at this moment, you can just accept this. And after finish the lecture slides of this chapter, I will talk about the derivation of the wave equation and how we can solve it. And then it will match this one. So here we talk about the EM wave mathematically. So in keeping this feature, we can deduce that an electromagnetic wave traveling along the x-axis has an electric field E and magnetic field B with the magnitudes and depend on x and t. So we have two formulas. So the first one is about the E field, and the second one is about the magnetic field. So we have E to be EM times sine of kx minus omega t, and B equals BM sine of kx minus omega t. So for both of the terms, we have the sign with the same argument. And here, of course, we have EM and EB are the amplitude of the E field and B field. And next, the electric field induces the magnetic field and vice versa. And inside the sine wave, inside the sine function, we have several variables. So the first one is called K, which you may not have seen it before, or you may not be familiar with it. But yeah, for X, omega t, and omega and t, these three variables you should be familiar, because X is nothing but the length. So yeah, and also the omega is the angular frequency. Omega is the angular frequency with the angular frequency, and the t should be the time. So nothing special. So the only special variable is the k, which is called the wave number, and the SI unit for it is meter inverse. Because inside the sinusoidal function, there shouldn't be any dimension for the argument of the sine function. For example, for the omega t, omega has the SI unit of radian per second. This is for omega. And for t, the SI unit should be, of course, s. So s and s will be cancelled. So omega t should have the SI unit to be radian. But of course, radian is not a dimension. It's dimensionless. It's just an angle. So you can also regard it as omega t equals 2 pi ft. 2 pi is, of course, a number, and frequency has a SI unit of hertz, which is X inverse, and T is S. So Hertz and s will cancel. Hertz and second will cancel. So it turns out that 2 pi ft is dimensionless. And likewise for kx, it should also be dimensionless, because x, here we have x to be the length, which is the x-axis component. So x has a SI unit of meter, and in order to make in order to make kx to be dimensionless, which means that x has a SI unit of meter, and in that case k should have a SI unit of a meter inverse, so that kx is dimensionless. So here is a meter inverse, and also k has a relationship as k equals 2 pi lambda, and that's why we call it a wave number, as the lambda is the wavelength of the EM wave. And you can simply imagine that if lambda is larger, which means that the wave number is smaller, and vice versa. So it is like we try to count how many waves within 1 meter. How many waves within 1 meter? We'll try to count how many waves. So k is called a wave number. If lambda is smaller, we can count more waves, so the wave number is larger. If the wavelength is longer, then within 1 meter there will be less number of waves, which means that the wave number will be smaller. So that's the meaning for the k. And next, we'll consider the wave speed, because the EM wave should be propagating in the space, so there should be a speed for this wave, and the speed will be omega over k, and another more famous equation is that c, and because this is an electromagnetic wave, its speed in vacuum is given by the symbol c rather than v. We'll always use c to represent the speed of light in the vacuum or in the air. The speed should be almost the same. So here c will satisfy this equation. C equals 1 over square root of mu naught epsilon naught. And as you have learned the electrostatic and also the magnetostatic, so you know epsilon naught is related to the electrostatics, or and the mu naught is related to the magnetism. So this speed of light related to this these two famous constant in the electromagnetism, and approximately c is equal to 3 times 10 to the 8th power, or more precisely 2 times 998 times 10 to the 8th power meter per second. Yeah, so all electromagnetic waves, including visible light, have the same speed. All electromagnetic waves have the same speed c in the vacuum or in the air. Okay, so other than that, the amplitude of the electric field and also the magnetic field also satisfy another relationship as this one, which is like EM over BM will be C. So for this 33.1, 33.2 is like EM and BM are just two independent variables, but actually they will always keep a fixed ratio between their magnitude, or of course So, and actually why it will be like this, we will actually derive it when we try to solving the wave equation. So let's just accept it at this moment. And the other variable is called the Poynting vector. So the weight per unit area at which the energy is transported via an electromagnetic wave is given by the Poynting vector. So actually, Poynting vector is a vector, so it should consist of two variables. One is the direction, and the other one is the magnitude. So so for the direction, it's nothing but the propagation direction of the EM wave. And previously, we already mentioned that E cross B should have the same direction as the propagation of the wave. So we have E cross B here. And actually, the magnitude of the Poynting vector is related to the rate per power at which the energy is transported. So it related to how many energy is transported per unit area, per unit time. So here it summarized that the direction of the Poynting vector of an electromagnetic wave at any point gives the wave direction of travel and the direction of energy transport at that point. Yeah, so this is the Poynting vector. And also, we also define the intensity of the wave. The intensity of the wave is defined by the S average. Because, as you know, the E field and the B field for the EM wave should be vary in a sinusoidal wave, which means that the Poynting vector itself should be somehow like the sinusoidal wave, and which means that it is time varying and also depending on the space. So, but here we consider the average energy transmitted by the EM wave, and here this is called the intensity, which is something like ERMS square over C mu naught. And like what we have learned in chapter 31, we have the ERMS is nothing but the EM over square root of 2, because E is a sinusoidal wave, so we cannot directly take the average, otherwise it will be 0. So we need to square it and then take the average over one period. So there will be a factor of 2, and then we need to take the square root of it, so that we have a factor of 1 over square root of 2. Yeah, so here we have a ERMS square over C mu naught. And also, we have another expression like here, which is I equals to PS over 4 pi R square. So you can consider this figure. So S is the source of the EM wave, and it tries to propagate in every direction. So for the original point, the power is PS, and as much as we consider the intensity and the energy or this power is propagating in every direction, so that as much as it propagates longer, which means the wavefront with a larger radius, then the same amount of power are separate in a larger spherical surface, which means that the power are equally distributed on the spherical with radius r. So we have I equals to PS over 4 pi r squared. Here, let's take a look at a sample problem. So here, when you look at the North Star Polaris, so you intercept light from a star at a distance of 431 light year. So light year is a unit of the length. Actually, the SI unit for the length should be meter, but yeah, when we talk about the star or some the color, so we'll use the distance. the unit of light year, which means the speed, the light goes, the length of the light goes for 1 year. Okay, and transmitting energy at the rate of 2.2 times 10 to the third power times that of our sun. So the sun, the power of the sun is 3 times 9 times 3.9 times 10 to the 26 watt, which is quite a large power. And of course, yeah, for the sun, it has many nuclear reaction to emit a large energy, and even for the North Star, emitting energy more than 1,000 times more than the the power of sun. And neglecting any atmosphere absorption, find the RMS value of the electric and magnetic field when the straight line reaches you. So here, on the previous page, we have I equals PS over 4 pi r square. So the intensity is separate on the surface of a sphere, and this intensity also equals to the ERMS square over mu naught C. So in this case, we can actually calculate the ERMS in terms of PS, R mu naught, and C. But before that, we try to convert the distance 431 light year into the SI unit meter. So 431 light year is like, we need to multiply it by the speed of light, which is 3 times 10 to the 8th power. And then for a year, we need to convert it into the second, which means that we should have 3,600 seconds for each hour. And then we have 24 hours per day. And then also we have 365.25 days per year. Not 365, but we still have 0.25 days because we have leap year every 4 years. So we need to count it as 365.25. Yeah, although it's still not so accurate, but yeah, we at least add it here. So the number will be 4.08 times 10 to the 18 power meter. Okay, so the next step is to find ERMS. So actually, ERMS, you can just put mu naught C to the left side and then take the square root. So we will have PS mu naught C over 4 pi r square. Just put mu naught C on the left hand side and then take the square root of the whole term. So we can just plug in all the values. PS should be 2 times 2 times 10 to the third power times P sun, which is 3.9 times 10 to the 26th power. And then mu naught is 4 pi times 10 to the minus 7 power. And then C is 3 times 10 to the 8th power, all over 4 pi r square is 4.08 times 10 to the 18th power. So we take the square root for the whole term. And this 110 turns out to be 1.24 times 10 to the minus 3rd power. You can actually use the V over M as the SI unit or N over C as the SI unit. So this is ERMS. And for BRMS, as much as we know, E over M, EM over BM should be C. And also we know that EM over square root of 2 is ERMS. Also, BM over square root of 2 is BRMS. In this case, C should be EM over BM, so we just divide both of them by square root of 2 so that the value doesn't change. And then actually EM over square root of 2 is nothing but ERMS. And BM over square root of 2 is BRMS. So that we will know BRMS is nothing but ERMS over C. And in the previous page, we know that ERMS is 1.24 times 10 to the minus third power, and C is 3 times 10 to the 8th power. So the BRMS should be 4.1 times 10 to the minus 12 power Tesla.